Hello everyone. Thanks for attending today's training. I am going to show some of the ways AADL can support trade studies and system-wide analysis for virtual integration. Some of our earlier training showed individual analyses performed on a model. However, when working with a system, we don't have the luxury of considering requirements in isolation. A successful mission system must satisfy many requirements, including different types of requirements. CAFFMAD is intended to help systems engineers understand and address change impact and relationships between components and system-level properties. For example, shown here is a ripple of change through a system due to updating a deprecated crypto algorithm to an approved modern version. When performing virtual integration, we can analyze multiple aspects of a model. We can also wrap these models and tools in our continuous virtual integration. This allows us to automatically reanalyze models as soon as we check updates into a model repository. So as the system is refined, you get immediate feedback on whether what you are doing still satisfies the system level requirements, such as separation between units of different criticality. One of the really neat things about AADL is that the language supports modeling different possible designs in the same model. You can use this for product line engineering, trade studies when developing a particular solution, or performing virtual integration to compare how different vendor solutions impact mission readiness. The results are shown in a dashboard here that give an analyst or technical manager insight into the impact. Later, I'll show you how this dashboard works. Our starting point for the demonstration is a Cubesat design scenario. A Cubesat is a tiny satellite measuring a mere 10 centimeters on a side. Many of the necessary subsystems are available off the shelf. What is appropriate for any particular Cubesat is, of course, mission specific. Since you can't physically maintain them once they launch, there's a strong incentive to get the designs right. Virtual integration can help reduce that risk. Now, even though a Cubesat is small, it must operate autonomously in harsh space environments to perform its mission. That means that the mutual interaction of all the subsystems that make up a Cubesat must, at the system level, satisfy the mission-driven requirements of all the properties shown on that first page, including security, resource demands, real-time performance, data integration, safety and reliability, as well as cost and schedule, of course. One property to satisfy is the end-to-end latency of critical flows. In this example, this is the time for a command from the ground station to get to the payload and then to be acknowledged and back to the ground station. The time it takes to do that depends on the speed of all the different components in the path, as well as effects from other components, such as other software running on a CPU or other data flowing on communication channels, and schedules for all those components. You of course need something more capable than a simple spreadsheet to calculate such values. So now we get to one of the many design challenges. Our basic goal is to get a sufficiently robust design that can handle radiation-induced upsets. What can I vary in my design to achieve that? The dense graph over on the left shows a tree of possible choices in just one version of the Cubesat. The insets dive into that design choice, and they show potential redundancy designs, such as simplex, duplex, or triplex designs for the control board. The developer can use CAFFMAD to select a particular configuration for some of the choices available in the model, and vary others. Here is an example of such a design subspace. We are evaluating redundancy designs of the command and data handling controller, the control board itself, different transceivers, and different algorithm designs. We have models of over 100 off-the-shelf components, so this is a small subspace compared to our possible commercial choices. After we select the Cubesat subspace, we then instruct the tool which analyses to perform. Here we ask it to analyze latency, utilization, separation, and reliability. Next, we save this design subspace specification and push it to our continuous integration server. That server builds each of the subspace points, runs each of the analysis tools on each point, and collates the reports into an XML file that it makes available on a web server. This is an example of our reconfigurable dashboard with results from the design subspace evaluation. This dashboard is a web-based application. It fetches the XML from the server and displays it according to user-specified rules in these display panels called widgets. The dashboard here includes widgets that are useful for developers, systems engineers, and technical management. This three-dimensional scatter plot shows reliability versus memory utilization versus CPU utilization of the command and data handling subsystem board. The developer can rotate this view to get a better idea of the perspective and how the points relate to each other. What's shown, each dot is a design point in that design subspace. You'll notice, of course, there are only 18 points here rather than the 48 specified in the design subspace. This is because not all design combinations will result in different reliability or utilization values. Some of that can be interpreted as reliability and utilization are not sensitive to those particular variations between those configurations. This can be good, since the developer therefore has some design flexibility if they're targeting a specific combination of reliability and utilization. Another thing to note is the display does not include reliability requirements or utilization limits. The intent of this display is to help the developer get a rough idea how the different design options relate to each other. The developer could optionally plot those limits on the same graph. Now, one thing to note is several of these design options use significantly more memory than the other options do. This might be due to the configurations that use memory-intensive algorithms that favor memory usage versus CPU performance. The developer can mouse over those points, at which point the widget displays the UUID of that particular design subspace point. The developer can use that UUID to further inspect those design points to figure out exactly what's going on. Another thing to note is that two design points over here have higher reliability and lower memory and CPU utilization than the rest of the design points. This would appear to be good, so the developer could mouse over those points also to get their UUIDs to further inspect those. If they look promising, the developer might further refine that particular configuration or those sets of configurations. This bar chart displays schedulability and utilization errors reported for each design point. The design points are on the x-axis. Schedulability utilization errors are shown in the bars. Ideally, this would be 0 across the board. What it shows is that the entire design subspace suffers some schedulability issues. This is not surprising, since it's early in the design cycle, and not all the issues have been worked out. It also shows a pattern where several of the configurations also have actual utilization that exceeds the allowed limit. This might indicate that these configurations will not meet the mission requirements. We can go back to the main dashboard. This particular bar chart shows actual latency of a critical flow versus the allowed latency of that flow. In this case, all the actual latencies are less than the budget, which is good. Scrolling down on the dashboard, we see the results of the multi-analysis domain separation. This shows the evolution of one aspect of safety and security requirement satisfaction over the design history of a single configuration. True or false of both the safety and security separation is on the y-axis. True means the test passed. The x-axis identifies the build number, which corresponds to the model updates over time. Builds earlier to 26 do not have information. This means the model did not model security or safety separation. Starting with build 26, the model has security information, but the initial designs failed, meaning security domains could interact without an intervening cross-domain solution that was designed to separate security domains. At build 29, The security design passed the separation test. The developer then switched to adding and analyzing safety. Build 31 shows that both safety and security were satisfied. Then at build 32, security fails. The reason it failed is the system was placed into an environment that violated the security requirements. The flaw was in the environment usage of the system rather than the system itself. And then back at 33 and forward, we now have the system in an appropriate environment. Continuing down, we have another three-dimensional scatter plot that shows the maximum CPU, memory, and bus utilization across the entire CubeSat. This display is intended to quickly provide the developer with a system-wide perspective of the available resources. This display shows that some of the designs exhibit low utilization for all of the resources. Others seem to be maxing out the resources. While this is the nature of resource-constrained embedded systems, this particular widget can help developers keep it under control. Technical management might also use this widget to help inform their risk management decisions. This chart here shows utilization of a specific processor versus what its allowed limit is over builds again. This line chart over here shows the trend of time over how long it takes to build the model and run the analysis tools. This sort of display can be useful for technical management to understand how program resources are being used at any point in time, as well as trends. If the time continues to grow over time, technical management might decide to get more resources. This chart is a table of all the results available in the XML. Each row corresponds to a design point. Your developer can go dig into more detail if they need it, if it's not displayed on one of the other charts. Since we don't know ahead of time what information will be useful to inform any particular trade study, we designed this dashboard to be easily reconfigurable. If a team comes up with widgets and dashboards they like, they can of course be shared. To add a new panel, the developer just selects Add Panel, opens it, and then they can configure it. They add a project information that gives a library of features, an artifact that points to, for instance, the Jenkins build that generates the XML, and they can select, are they looking over multiple builds in design history, or are they just looking at the latest? They can then pick many different types of displays, and then for each display type that they have, say a bar chart or something else, they can add in information and traces to that. It's very flexible. So overall, this capability allows you to look at lots of different types of data simultaneously and assess where your system's at any point in time. Thank you.